And this particular piece is about limits involving infinity. So this is section 2.5. Limits involving infinity. So basically two types, okay? And you'll see this again in Calc 2. You're looking for vertical and horizontal asymptotes, basically, right? So if I said to you the limit as x goes to 0 of 1 over x squared, well, of course, you could see that this is the case, one of the cases where the limit doesn't exist, where it's unbounded, right? So you can kind of imagine this from the right. What would I get from the right? Where am I walking to from the right? Infinity. And then where am I walking from the left? Infinity. And you say, well, hey, it's equal left and right, but it's got to be a real number, right? So we will say that this is infinite, but better yet is to say it does not exist. So we want to tell whether it goes to positive infinity or negative infinity, and we kind of use this improper notation here, again, because I can't use an equal sign unless I have a number, but we'll say it goes to infinity, and then we'll write DNE, does not exist, okay? So for example, look at the limit as x goes to infinity. So you can see where I'm talking about involving infinity. I might have an answer of infinity or an x value going to infinity, right, of e to the minus x. Yes? And where is that limit going? 0. So you can have the infinity as a result, a plus or minus. You could have the limit going to plus or minus infinity, okay? So how do I deal with this? Obviously, numerically works very well. Graphically works very well. But there's two algebraic ways that we're going to be looking at it. One of them I'll teach you today. One of them I'll teach you tomorrow, called L'Hopital's rule. I don't know if any of you have heard of L'Hopital's rule before. No? Okay. That's fine. So we have one particular theorem that we're going to kind of just memorize, and that is the limit as x goes to plus or minus infinity of 1 over x to the n is equal to 0 for n in the natural numbers, right? 1, 2, 3, etc. Now that theorem I can prove this with the delta epsilon, but it really kind of seems silly to have to do it, right? If I look at 1 over x squared, etc., right? I mean, it's pretty clearly whether I have this odd function, right? X to the n is odd, right? Or x to the n is even. It's pretty obvious graphically that it's going to 0. Do you agree? Okay. So I'm going to use this particular theorem to show some limits at infinity for that are algebraic. Okay? So let's go to the book. For this particular section, I really like 15 to 35. This is page 133. It's section 2.5. What does our homework say for our 15 and 35? Thank you. And 2.5. Say again? The ones that are handed in are always odd. And of course, the only ones you have answers to are odd. So, yeah, do odd ones. Yep. Let me do 22. 22 and 30 I'll do. So I've got the limit as x goes to infinity of 3x plus 5 over x minus 4. Now we did this in pre-calc. So this is a vertical, what we're talking about is horizontal asymptote here. So what's the horizontal asymptote in this function? Almost 3. Vertical asymptote is 4. Yep. Nice, but we're going to show a little calculus to get the same result, right? And so what we're going to do is we're going to call star 3x plus 5 over x minus 4. And I'm going to divide by the highest power of x. So that is x to the 1. So I'm dividing upstairs by x and downstairs by x. So I get 3 plus 5 over x over 1 minus 4 over x. And that's what I'm going to apply my limit to. So the limit as x goes to infinity of star is the limit as x goes to infinity of 3 plus 5 over x over 1 minus 4 over x. But I know where both of those go. I know where both of those go. Where do they go? So out as I go to infinity, what's happening to 1 over x? Where's it going? It's going to 0, right? So that our theorem just said that. I get 3 plus 0 over 1 minus 0, so I get 3 over 1, or 3. So I'm just applying that one little theorem that if I have something over x to any power, right? If I have a number over x to the 1, or x squared, or x cubed, or x, etc., I know that goes to 0. I said I wanted to do 30, but I don't think I do. Let me try 38. Again, numerically, graphically, these are very easy, right? If I'm letting x go to infinity, I'm doing like 100, 1,000, 10,000, a million, and I'm just seeing where it's going, right? But let's look at this one. I have f of x equals square root of 2x squared plus 1 over 3x plus 5. 38. Well, graphically, I certainly can look at this, but I can use my same process. What's the highest power of x that I have? X squared, I would expect you to say, but it's not x squared, it's what? Just x, because that x squared is inside the radical. So I want to divide by square root of 1 over x squared, top and bottom. Again, I'm picking the highest power I have in numerator or denominator. So what happens upstairs? I get the square root of 2x squared over x squared plus 1 over x squared. Make sure we agree with that. But what happens downstairs? What's the square root of 1 over x squared? That's just 1 over x. So I get 3x over x plus 5 over x. So I have a theorem already. I know as x goes to infinity of those pieces, what happens to 1 over x squared? Where does it go? Where does 1 over x squared go as x goes to infinity? 0. Where does 5 over x go as x goes to infinity? 0. So I get square root of 2 plus 0 over 3 plus 0. So square root of 2 over 3. Um, 5 over x, right? Yep. That's it. That section is that easy. It really is that easy. Do I assign anything from that section? No. Why don't I assign anything from that section? It's too easy. Nice, let's take some quizzes. Okay, good. So I want to be thinking about, and I like to go back to this mother function thought. I don't know if I've had this conversation with you all, but the mother downstairs is 3x. If I look at 3x and 3x plus 5 in the long run, guess what? They're both going to the same place. They're this way, right? And if I look at the square root of 2x squared plus 1, and I just take the mother piece of it, square root of 2x squared, which becomes square root of 2 times x, it in the long run, it behaves exactly the same way as that original function. Kind of like we all become our parents, if you haven't already realized that yet. You will soon. By 30, for sure, you'll be like, oh my God, I can't believe I do what my mother does or my father does. So in the long run, we're just really thinking of, right, what's that highest power? So I can see the highest power I have upstairs is an x, the highest power I have downstairs is an x. So I'm really dividing by x, 1 over x, right? But when I put that inside the square root, it becomes 1 over x squared. Yeah. Yes, exactly. So inside I'm dividing by x squared, outside I'm dividing by x. So inside I'll divide by x squared, right? Outside I'll divide by x because this is just 1 over x. Square root of 1 over x squared is 1 over x. It's weird. It's weird. Yeah. Yeah. In calc, at the end of our class, it'll come into play. But you'll see, I'm really just going to use this whole idea of 1 over x goes to, as x goes to infinity, 1 over x goes to 0, 1 over x squared goes to 0, 1 over x cubed goes to 0, etc. Right? That's what we really need to remember for the end of the semester. Nice.